This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
So, your expertise is a bit different than most of your colleagues there, and a little more specific and frankly cool sounding. You specialize in biogeotechnics, which sounds like something sci-fi. Can you describe kind of what that is and how you use that to help with the natural hazards engineering side of things?
Yeah, it's a fun story. It's the whole world of biogeotechnics came about kind of around 2003, 2004. We started dabbling in it, and we're one of kind of the early explorers, if you will, of this whole concept of trying to link biology and biological aspects of the natural world with engineering and the hard fixing of things, so to speak. And we were involved in it early on. There's a few other people in the US, a few other people internationally that kind of have dabbled in it. And now in the last 5 years, 10 years in particular, it's really grown and become, a lot of people are kind of working in that space. And so for me, when we started out, we were just trying to do one thing, and all we were trying to do was trying to learn how to control bacterial activity in the ground through the environment, through the chemistry in the pore fluid, and to facilitate the bacterial activity, and then for them to facilitate precipitating or binding particles together. Wow. And in order to make that become cement or cemented soils, actually, there's another, here you go. If we want to change out our backgrounds.
Oh, there we go.
That's what happens like at the small scale, right? Those are individual sand grains. You can't see the bacteria, but then the binding between the particles that you can see there in this kind of lighter color, that's actually what we're doing. And we're cementing those pieces together. So this began kind of as, hey, this is a crazy idea. Let's spend some time trying it out. And it worked.
So you found these bacteria that under certain conditions essentially make the sand particles around them bind together like cement. Yeah,
they will bind and they will become very stiff and very rigid. And so you're essentially creating a sandstone.
Wow.
Type material. And so that was something, the first test, it took 18 months to get like one test to work. And that was the first master's thesis. And then it kind of grew from there, and we tried and kind of went on. And since then, the whole field's kind of split into two parts. There's one part which is called biomediated ground improvement, if you will, or biomediated geotechnics. And really there, the biology is mediating some natural process in order to change the engineering properties. So that's like what I just described is we have bacteria mediating a chemical reaction, binding particles together rigidly. And now we have a rigid, stiff block, which has high shear wave velocity, high stiffness, high strength, dilatancy, etc. And it is much more resistant to liquefaction.
Wow.
And so that was kind of the first one. And then about 5 years later, people started saying, okay, well, how about bioinspired or biomimicry, as people might have heard of? And that's different. That's
very different.
Yeah, that's different. That's saying I see ways in which biological organisms behave in nature, and they do things really efficiently. Maybe I can study and I can understand the form, the function, the shape, the behavior of those things, and I can translate it over. So a cool example of that, actually, it comes from research my colleague Alejandro Martinez is doing. And in that one, they have studied the underbelly of snakes, and they have recognized that the belly of snakes are different based off of what material they move across, because they need friction in different ways. Yeah. So they look at tree snakes. They actually got preserved snake specimens from a museum, scan the bellies of them, and they figure out like what's the texture of it. They analyzed all those shapes. They wrote some software to characterize them. They extracted the important pieces. They've taken those important pieces and then they have used them on piles and pile foundations to change the texture of the surface to make it behave much more efficiently than what we do ordinarily day in and day out. So those are the two. It's like biomediated. Let's let biology control engineering process, which is hard for engineers to become comfortable with.
Right.
And then the other one is let's make stuff that looks or functions like natural processes, and we'll try those out and try to gain some efficiency in performance, both of which are kind of way outside the norm of construction-driven, steel, concrete, high energy-driven, brute force contracting, building of stuff. And so it's been a really fun space to explore, and it's always kind of mind-stretching and make you think of things in a new way. So fun.
The first time I came across something like that was a few years ago. Someone was looking at like thermal efficiency of termite mounds and how to translate that to architecture and do like passive cooling instead of more active, HVAC and desert environments. I'm like, that is wacky.
Yeah. A lot, what's really interesting is a lot of these processes are so much more efficient. They're efficient in how they are built. They have the benefit of being able to grow naturally. So that part's really different, but they're also very efficient in terms of their performance. So if you take whatever performance metric you want and you normalize that by the size of the object or the total mass of material that you're using or whatever else, they're factors of efficiency. Sometimes we see things 20, 40 times more efficient than what we do.
Wow. And
so then it makes you sit there and say, okay, well, we know how to build things the way that we do currently really safely. So we know how to do piles, and we can make them be really, really safe. But then you can say, okay, but trees can do this also. And trees stand up pretty well, and they can handle high winds, and they can handle a variety of conditions. And in fact, their capacity in terms of, say, pull-out capacity is about 20 to 40 times better than our piles are.
Wow.
On a per mass basis or a per mass comparison.
Wow.
So then you gotta say, well, we're never gonna do exactly the same thing that trees are, but if we have a factor of 10 or 20, certainly we can improve what we do.
Yeah.
And so that's what we're trying to explore. We're trying to explore that space and say, how could we push more towards biological systems that can be that much more efficient?
That's cool.
It's neat. And the creativity that's required and the creativity that you see in students doing research in it, and when you get colleagues together, it's really neat.
Thanks for listening to today's episode of Design Safe Radio. This show is sponsored by the National Science Foundation grant number 1612144. You can subscribe to Design Safe Radio on iTunes, Stitcher, or wherever you find your podcasts. Please leave us a review so we can improve the show. Please also help others find our episodes in iTunes. Thanks for your feedback and support. You can find out more about NHERI at designsafe-ci.org, on Facebook at Design Safe Radio, or on Twitter at NHERI Design Safe.